All right, 10a, the derivative of the following functions. We got two terms. Is that going to be a problem? No, because we know we could just take the derivative of terms individually and then just work down the line. So the left side becomes dy dx, or y prime. What do we do with the 2? Does it go to 0? Good. It is not a if it were 2 plus sign, it would be its own term. It would be 0. But it's a constant multiple, so it just goes along for the ride. And then the derivative of sine of x is cosine of x, of course. And then the derivative of plus 7 is 0. Now, let's say I wrote this. Just kind of reminds me. This would be wrong, of course. But if I write it like that, what are you assuming we're taking the cosine of? X or x plus 7? In other words, is that cosine of x plus 7? Or is that cosine of x plus 7? If I don't write any parentheses. Good. We infer it to be the first one, right? So if you ever have more than one term after like a log or a cosine, and you want it to be part of the angle or argument, you got to put in parentheses. If it were factors, we would assume that it goes there. So that would be like cosine of 2x. We would assume that that's not cosine of 2 times x. But for multiple terms, we would. So 7 goes to 0, so there's the answer. Yeah, good. Letter B. Two terms. Left side, f prime of x. Derivative of x is 1. And then the derivative of cosine is negative sine. Good. If it starts with co, it's going to have a negative derivative. Letter C. We got a product of two variable functions. We do not know the product rule yet. So this identity that I gave you as a hint could help. So the nice thing about the identity is it works both ways. So essentially 2 sine of blob times cosine of blob is equal to sine of twice the blob. Right? It doesn't have to be x, it can be anything. I have a blob. My blob is x halves. So this 2 that's there, I'm just going to rewrite them. Sine of blob, cosine of blob. Oh, maybe I don't need to rewrite him. I can actually incorporate him. Notice I have that right there. So 2 sine blob, cosine blob. Let me get rid of him here. If I take all of that together, that becomes sine of twice the blob. Well, that's twice x halves. And so that turns into, of course, sine of just plain old x. And notice as I'm rewriting it, I'm just using g. And now I'm ready. G prime is cosine. So 2 sine of x halves, cosine of x halves is just sine of x in disguise. Pretty cool. Halloween's coming up, right? Halloween's coming up. But not, Hoko is coming up first, right? Homecoming. All right, any comments or questions on that? You got your 2 new rules down pat, right? Sine is cosine is negative sine. All right, example 11. If sine of x is the function, find the following. The slope of the graph at 0. We kind of did this yesterday, kind of did a little extra thing to see graphically what was happening. The slope of sine at 0, do y'all remember the angle at which I told you it launched out at? 1, good. Well, yeah, a slope of 1, an angle of pi fourths or 45 degrees. So we'll prove that, right? So if I want to find the slope at a point, slope at a point, that's what? Derivative. So I'm looking for f prime of 0, but before I find f prime of 0, I got to find f prime of x. So there it is. There's f prime of x. It's cosine. And now we can plug in a 0, and we show that on both sides. We get f prime of 0, and you can plug in cosine of 0 like that, and in a free response, you're done. Or in this case, we'll keep going. It's 1. So there it is. We just proved that sine, just like tangent, launches out at an angle of 1. And that's why sine and tangent behave the same way near 0 in terms of limits. All right, what's f prime of 7 pi 6? Well, you can see this is kind of a nice way now to review the unit circle. It's just going to be the derivative, which is cosine of 7 pi 6. Free response, you're done. Multiple choice, we write down what? Negative square root of 3 over 2. That would be a great answer choice on a test. Is that the right answer? Yeah, because we're over here in quadrant 3. The right answers always make great answers. Oh, he was adding. Yeah. No, he's right. He's right. I know tone can be misleading, right? But that's just why you need to be more sure of yourself. Okay, very good. And then it says, for all x in the half-open interval from 0 inclusive up to 2 pi non-inclusive, where the graph has horizontal tangent lines that we're trying to find, where the graph has horizontal tangent lines. So working backwards from where we need to be, a horizontal tangent line, how does that relate to a derivative? That's the zero slope. So we want f prime of x to equal 0. So if you just say f prime of x equals 0, you've earned a check on a free response. And you can do it that way, or you can actually take f prime, which we know is cosine, and or you could do that, cosine of x equals 0. So without the first line, you can earn that check doing that. All right, so now we divide both sides by cosine, bless you. And the cos divides out, and we're left with 0 divided by anything is 0, right? Yeah, boy, doesn't that's funny. Okay, cool. So how do we solve for cosine? Or for x, how do we get rid of the cosine? We would technically take the inverse cosine, the operation, not the function of both sides. But that's not how we typically solve these. We just kind of do it in our head, right? I want to know between 0 and 2 pi, that's once around the unit circle, where are the cosine values equal to 0? Pi halves and 3 pi halves would make a good answer choice, because it's also correct. Yeah. So at both of those. So those are the locations where we have horizontal tangent lines. Could we write the equations of the horizontal tangent lines there? We could. Let's do that. What are the equations of the horizontal tangent lines? Oh, yeah, how would we do that? Is it y equals 0 because they're horizontal, their slope is 0? Right. We would need to find the y value, right? So we would have to plug those back in up to the original one. So that's just the sine value. All right. So if we wanted the ordered pairs, the actual points, it would be pi halves, comma, sine of pi halves, which is 1, and then 3 pi halves, comma, sine of 3 pi halves, which is negative 1. And since those are the ordered pairs, the horizontal lines would be y equals 1 and y equals negative 1. And of course, we know that to be true because we know what the graph of Sahala looks like. We did it yesterday. So this would just be up at the local max and local mins. All right. Sweet. So now we know those rules. Pretty good. And we always know the unit circle. So here's an application of the power rule of which Newton would be proud. Motion. Okay. So we know that the derivative of a function at a point gives us two equivalent things. The slope of the tangent line at that point, that's the Leibnizian perspective. And then the instantaneous rate of change at that point in time or that instant, that's the Newtonian perspective. And of course, Newton was the motion guy, the three laws of motion. It was the impetus for his discovery of calculus. So we're going to talk a little bit about kinematics right here. But if we let h of t be the position function for some object at time t, we use a lot of different letters for position. If it's a falling object, which is what we're going to do, if it's a falling object, h is a good letter to use for position because it gives you the height. Right, good. If you're talking about like horizontal motion, you could use x of t if you're moving on the horizontal axis. We'll see that later in the year. If you're moving on the vertical axis, we could use y of t. That'd be, sometimes it says like a particle is moving up and down on the y-axis. But if we're off the coordinate plane, a letter that we typically use for position is S, right? For position, I guess that's where it comes from. No, I think it's like Greek for strata, like a statute mile. Strata maybe. Distance or something. Okay, so those are the letters we typically use. But in this case, we're letting h be the position of a function of t. V of t is the instantaneous velocity, and a of t is its instantaneous acceleration. We can relate all three of those to each other by this one equation. Okay, so let's start on this one here. It says that v prime of t equals a of t. What that says is that the instantaneous rate of change of velocity is instantaneous acceleration. Yeah. And it's also true for average. The average velocity, if you take the average of the velocities you'll get over an interval, you'll get the average acceleration on that interval. The average rate of change, of velocity on an interval. This right here is a double prime mark. Double prime. And that we kind of abandoned the prime notation after a while. You can imagine if we took the 100th derivative, you would have 100 primes there. But with the double prime, it's just hash, all right, prime. So what we're saying then is two things here. The first derivative of position is velocity, okay? And the second derivative of position is acceleration. So this all ties them together. The instantaneous rate of change of position is velocity, and the instantaneous rate of change of velocity is acceleration. So if you memorize your kinematic equations, you probably memorized the falling objects near Earth to be the following. It was negative 1/2 little g times t squared plus v sub o, maybe you used, or v sub I, used I, okay, v sub I sub t plus, and then it would be h sub I or h sub o. So that is your position of a falling object near the surface of the Earth, and little g could be either 32 feet per second squared, or it could be 9.8 meters per second squared, or for AP purposes, it could be 10, right, meters per second squared. I think they kind of went with that so you could do more calculations without a calculator. But they're roughly the same, and that's the, of course, everyone knows that is what little g is, not the rapper out of Compton. He is the gravitational constant. Gravitational constant. And that's an empirical value that can actually be measured, right? As objects fall near the surface of the Earth, their velocity increases by roughly 10 meters every second, meters per second, sorry, every second that it falls. You really don't need to memorize all three of them, because what we're saying here then is if you want the instantaneous velocity equation, here's all you need. H prime of t is, now, what we are about to do, if you listen very carefully, you will hear Galileo not only grumble, he is kicking out of his coffin. He's trying to scrape his way to the top to get over here. Because what we're about to do, he was never able to do. He spent his life trying to figure out how to do this, but he never was able to figure it out. The instantaneous rate of change of position is velocity. And now because we have three terms, it's power rule ready, isn't it? So if that's true, and it is, let's take the derivative. 2 times negative 1/2 is negative 1. So we end up with negative g, which is a constant, times t to the first, right? So we multiply and subtract. Plus, that's t to the first, so that just becomes plus v sub I. Initial velocity is what that is, or velocity at time 0. Plus, what's the derivative of h sub I, which is the initial height? 0. There it is. That's it. For falling objects near the surface of the Earth, if you want to know how fast they're falling at any given time, that's the formula you use. It seems so simple, right? Do you think Galileo knew how to multiply and subtract? Sure he did. Do you think he knew that if he multiplied and subtracted in that capacity, it would give him what he was looking for? Absolutely not. Okay? And now if we take the second derivative of position, that would be the first derivative of velocity, which we call acceleration, a of t. We'll do the power rule one more time. This is how we find higher order derivatives. We just keep going. So what would be the derivative of negative gt? Negative g, and then v sub I now is the initial velocity. It's a constant. It goes away. And we are left with the acceleration of a falling object near the surface of the Earth is negative g, which is the gravitational constant. Yeah. Now sometimes g is listed as a negative number. If you're using g as a negative number, then the negative isn't in the equation. Okay. So it kind of depends how you use it. But yeah, so believe it or not, these equations did not come into existence in this order. They actually came into existence in this order. The gravitational constant was empirically measured, and then from there they did what's called anti-differentiation, or they solved a differential equation. They went backwards from there by undoing the derivative to get to the velocity. And then they undid the velocity, they being mathematicians. I don't know who exactly gets credit. And then you get that, you anti-differentiate to get h of t. And that's what we're going to be starting hopefully right before Christmas and the first part of the second semester. It's the other half of the house of calculus, that's integral calculus. Okay, now the father of integral calculus is in the far right corner. That's Archimedes. So he was doing integration techniques that weren't really calculus way back in ancient Greece. 200, 300 BC. But the father of differential calculus, of course, much, much later, 1800 years later maybe, Newton and Leibniz. All right, so let's look at this right here. Example 12. A calculus textbook. Now, let's stop right there. What the heck is that? What is a textbook? Well, if you ever go to like an educational museum, you'll see textbooks on display. We used to have them, and basically it was everything that's in your iPad for that subject, but it was outside the iPad. You could take it with you wherever you went. And it was stolen from a museum. There you go. And taken to the top of a 400-foot tower with the sole purpose of being dropped down to the unforgiving pavement below. Okay? So this was known to happen in the past. Students would be frustrated with calculus, and they would take out their anger on the textbook, and it gave them some kind of catharsis or some kind of relief. Unfair to the textbook, of course, right? If the height h of t at any time t seconds during its brief but painful plummet to Earth, so it's not only painful when it hits, it's painful as it falls, it says. It's sad. It's given by this equation, right? So if you look at what we have there, we're using little g to be 32 feet per second squared. So 32 times a half gives you the negative 16. There is no t term, so that means the initial velocity is missing. It must be what? 0. So we're not that angry that we're taking it and throwing it down with some initial force or throwing it up above our head. We're simply holding it out over the edge and letting go. So 400 is the initial height. So you can come up with that equation on your own if you know this position kinematic. All right, but I gave it to you. Answer the following questions regarding, what time is it? 7, okay, got it. Yeah. Okay, for how many actual seconds was the book falling? And I say actual because to the book, it felt like an eternity. Okay? Okay, and it says how many you feel like. We answered the second one. Like an eternity. Like infinity. Hours. Okay, we'll put units there. But how long was it actually falling? All right, so how are we going to go about doing that? We can't ask the book. It didn't feel like talking after the fall. It survived, in case you're wondering, or we wouldn't be doing this problem. Absolutely, right. We need something to work with. So what we do know about the book is that when it hits the ground, its height, its position is 0. So what we're going to do to solve for t is we'll let h of t equal 0. So again, you always want to show the equation you're solving. You can earn it like that. That would earn that check because the function's name is h. Or I should say, you could go ahead and set the expression that is h of t equal to 0 because without a calculator, that's what you're going to have to work with. So either one of those would earn you the first check. So now let's solve that. We get negative 16t squared equals negative 400. So t squared would equal negative over negative is positive, so we're going to get 400 over 16. And does it simplify? 25? Okay. So t would equal 25. Or t squared should. Sorry. Getting ahead of myself. And now we'll take the square root of both sides. And we always want to consider, this is important, when we take the square root or we take the fourth root or we take the eventh root, we always want to at least consider plus or minus. So it's either going to be negative 5 seconds or positive 5 seconds. Now sometimes negative time values are relevant, right? If we arrived upon a situation as it was already in place, then a negative time would be extrapolating backwards before we got there. But in this case, I hate to say it, but we were the ones dropping the book. We were there when it started, so the negative time doesn't make sense here. We started our stopwatch right when we dropped it. So it was actually in the air for 5 seconds. Now, what if you don't know 400 divided by 16 is 25? What could you do? One of two things. You could go old school division, right? 16 times 2 is 32. Subtract, you get 8, and then 16, then you can true trial, and it goes in 25. Could you just leave it, though, as 416? And then if you take the square root of that, you get plus or minus the square root of 416. That would be fine for a free response, of course, then, if you got rid of the negative one, which I'll do right now. What's the square root of 400? 20, right? And the square root of 16 is 4. So you get the same answer. I already got rid of the negative answer. Now, on any final answer with when units are around, make sure you put units on your final answer. Now, we should answer this with a closing statement, but if you don't, then the bottom line, t equals 5 seconds, becomes your answer to the question. But it's always nice to say, so the book was falling for an iPad, and they eloped, and the rest is history. That's a different kind of falling. That's falling in love. The book was falling for 5 seconds. Okay, cool. That's a long time. 400 feet, that's like, that's almost as tall as the band tower in the back, right? Almost, right? Yeah, Mr. Day was up the other day, and I could barely see him. No, 400 foot's pretty dang tall, right? It's not even as tall as like the lights that we have at the stadium, where several years ago a guy climbed up, and it made the news, and we got him down okay. But yeah, he climbed up to the lights at the Unicorn Stadium. That's still not 400, but it's tall, right? All right, we need to go on part B, because I'm squandering time. What was the velocity of the book in feet per second the instant it hit the pavement? All right, is that average rate of change or instantaneous rate of change? That's instantaneous. How do we know? At the instant it hit the pavement. Gosh dang it. Okay, so I need to find the derivative of h, which is negative 32t plus 0. Right? I just took the derivative. So I can call it h prime of t. I never even have to call it v of t. But what's nice, and you'll see me doing this often, is if you put h prime of t and then rename that function v of t, now you can refer throughout the rest of the problem as the velocity function as v of t. You don't want to just start calling it v of t if you've never defined it. That's enough to define it. So now notice that function requires me to input a value of t. What value of t am I supposed to put in? 5. Yeah, we just found that. So now I'm just underneath there, I'm going to put v of 5 is negative 32 times 5, which gives me negative 160, and then I'll put units, feet per second. So there's two ways to read that. In the final minute, there's two ways to read that. You can say that at t equals 5 seconds, comma, the book's position was decreasing, right? Anytime we have a derivative that's negative, that means the function is decreasing. Well, that's the derivative of position. Or the height of the book is decreasing by 160 feet every second, right? That's what that means. But we can also interpret that as at t equals 5 seconds, the book hits the ground at 160 feet per second. So there's a little bit of refinement of the human language that we can use to make it sound better. But from the straightforward engineering perspective, we could just say at t equals 5 seconds, the book's position or height is decreasing by positive 160 feet each second. Okay, so we're going to be doing a lot of sentences like that throughout the year, and I always encourage you just to kind of stick with that straightforward engineering approach instead of trying to like reword it, you know, using like adjectives and modifiers and dangling participles and whatever. Because if you deviate from that recipe, you might misspeak or say something that's incorrect. So anyway, have a super duper lunch.